All right, so hi everyone, and welcome to our little workshop today. We're going to be going over basically identifying acids and bases, and then we're going to start calculating pH and pOH of solutions. So let's get started. So the Arrhenius definition of acids and bases. So the Arrhenius definition of an acid is one that increases the concentration of H plus in a solution. And remember that an H plus is just simply a proton. And on the other hand, the Arrhenius base definition is one that increases the concentration of OH minus in a solution. And so the OH minus is the hydroxide ion. And so when we write these acids, these ions of H plus and OH minus, I should mention that the hydrogen ion almost rarely actually exists by itself. It is usually going to be in solution. So you can see this little reaction down here. We can see the H plus reacting with H2O to get us H3O plus. This is going to be the hydronium. And H2O is just water. And you may often commonly see it just written as H plus. It is correct, but it's not really an accurate representation because, like I said earlier, hydrogen ions, the proton itself hardly ever exists by itself in nature. One common place you'll probably only be able to find a lot of H plus is probably on like the surface of the sun. So it's not a really accurate representation to just write only H plus. So here are some examples of some common Arrhenius acids. The first one we have is HF. This is hydrofluoric acid. It's a pretty strong acid. If you've ever seen TV shows like Breaking Bad, yeah, you may have seen hydrofluoric acid. It can dissolve bones and flesh, and it very easily seeps through your skin. And so it can cause a lot of severe tissue damage. So if we look at the HF acid, hydrofluoric acid, we can see that it's capable of increasing the hydrogen, the H plus concentration in a solution because it can break up into the H plus ion and the F minus, which is a fluoride ion. And so this is going to help make it the Arrhenius, it satisfies the Arrhenius acid definition because when this dissociates, it's going to form the H plus ion. Another example of an Arrhenius acid we have is HCl. HCl is hydrochloric acid. So this is hydrochloric acid. So this is another common acid. It breaks up into H plus and the chloride ion. And so you might commonly find hydrochloric acid. It is often secreted in your stomach lining. Another example of a Arrhenius acid is H2SO4, which is sulfuric acid. We can see that it will break up into the H plus and also an HSO4 minus ion. So when H2SO4 is like placed in like a solution, it will dissociate into the H plus and the HSO4. Common place you might find the H2SO4 is it does naturally exist and makes up the clouds on Venus. And finally, we have one more example, HNO3. This is nitric acid. This will break up into the H plus and the NO3 minus. And so a common use of HNO3, you might see it used in organic synthesis. So people will use this to create something called trinitrotoluene. Some people might be more familiar with it as TNT, which is an explosive. So some examples of Arrhenius bases. So Arrhenius bases, if you remember, they will increase the concentration of the hydroxide ion, which is OH minus. So here are some examples. A lot of them you'll notice that the Arrhenius bases, you'll usually see a component that has an OH in it. So like you can see all these examples, they have a very distinct OH in it. So this first one, it is NaOH. This is sodium hydroxide. It breaks up into Na plus and the OH minus. And so we can see here, there's OH minus. And another common use for sodium hydroxide, you might see it in like your soaps, lye, and drain cleaner and all that stuff. Another example we have of an Arrhenius base is potassium hydroxide. So potassium hydroxide breaks up into the potassium ion and the hydroxide ion. So here we can see that the potassium hydroxide breaks up into K plus and OH minus. And one common use that you might see potassium hydroxide is in like shaving creams or leather tanning. So it's very good at like weakening the follicles of like hair and something. So it's very effective for tanning. Our next example is calcium hydroxide. This is Ca and then in parentheses OH2. This is going to be breaking up into the Ca, and there's also two components of the OH. So it's like OH minus. So these are like the main ions that we'll be seeing. We can see here it'll increase the concentration of OH minus when it dissociates. And so a common use of calcium hydroxide, I think some people use it for like pickling your food or for sewage treatment or water treatment. And finally, we have magnesium hydroxide. This is MgOH2. So this will break up into primarily the Mg and the OH minus. And we can see once again, there's an OH minus, which is going to increase the concentration of hydroxide ions. And one common case where you might see magnesium hydroxide is in something called milk of magnesia, which is something you might drink if you have like a heartburn or something. It's a pretty good antacid and also functions as like a laxative. So moving on, there's actually multiple definitions of acids and bases. So another definition that you'll want to be familiar with is the Bronsted-Lowry definition. And so the Bronsted-Lowry definition of acids and bases basically states that the Bronsted-Lowry acid is going to function as the hydrogen donor or proton donor, more or less. So this is going to function as the hydrogen donor, whereas the Bronsted-Lowry acid and the Bronsted-Lowry base, my bad, is going to function as the hydrogen ion acceptor, or like the proton acceptor. So if we look at this bottom example here, you can probably tell from that previous slide that I mentioned that HF is going to be a hydrofluoric acid. So naturally, you'll probably assume that the hydrofluoric acid is going to be our Bronsted-Lowry acid, which is true in this case. And so basically what's going to happen is if we compare the reactants or the starting material to the products, what we can see here is that this fluorine is going to be alone in the product. And that is because it's going to have given away its hydrogen to the water. So we can see that the product here, this H3O plus, is really just a water, but with an extra H plus on it. So by definition, we know that the hydrofluoric acid donated its H plus. So because of that, it will function as the Bronsted-Lowry acid. Now, on the other hand, we have H2O. H2O is going to be our Bronsted-Lowry base. So I'm going to write it as BB. And it is going to be the Bronsted-Lowry base because if we compare the starting material and the product, we will have noticed that the water is going to have accepted one of the H plus ions. So if we compare the formula, this is H2O, and in the product, this is going to be H3O plus. So it gained a H plus. In other words, it accepted an H plus. So because of that, the final result is basically hydrofluoric acid is our Bronsted-Lowry acid. Water will function as our Bronsted-Lowry base. I should mention that water is amphiprotic. I believe that's the term. And that basically means that it can function as both an acid and a base. It really depends on the situation. So moving on, this doesn't really go back to like the definition of an acid or a base. It's more like a continuation. So another part of these reactions, or when you look at acids and bases, is that you also want to pay attention to the conjugate acid and the conjugate base. So the conjugate acid, and if we're just going to look at this, assuming that we're following the Bronsted-Lowry definition, it is going to be the compound that is formed after the reaction when the acid donates a proton to the base. So if you remember from our previous slide, we used HNO3. This was nitric acid. So this first one is nitric acid. So we know that this is going to be the acid. And because of that, this would probably function as the base. Because if you compare the starting material and the product, we'll see that the HNO3 will have given away its hydrogen right here, all the way to this water right here. And then as a result, this NO3 minus is going to have lost its hydrogen or the proton. So this is going to be the proton, HNO3 is going to be the proton donor, while we have H2O functioning as our proton acceptor. Now, what we can do is we can look at like the reverse reaction. So let's say I were to draw an arrow that also goes backwards. So if we were to look at this reaction from the backwards direction, we can also see that H3O plus and NO3, if we go in the backwards direction, we can see that H3O plus could technically give away its proton to the NO3, and then you will form basically the starting material again. And because it's giving away its proton, it is functioning as like an acid. And in the product here, we can see this is going to function as like the base, because this is going to be the one that accepted the proton. But instead of just saying acid and base, we want to be more precise. What we would say is that with respect to the definition of conjugate acids and bases, the compound that is formed after the reaction is going to be the conjugate acid and the conjugate base. So we can indicate it by saying H3O plus is going to be our conjugate acid that is formed, and NO3 minus is going to be our conjugate base that is formed. So like we could really actually write this in the reverse direction. So let's say I were to draw out or write out this reaction backwards. I could write something like H3O plus and NO3 minus gets us HNO3 and H2O. So if we look at it, we can see that H2O plus, it can donate that hydrogen to NO3 to form HNO3. So because it can donate the hydrogen, this can function as the acid. And this, because it accepts the proton, functions as the base. Making this, because it can, if you look at the reverse direction, it can actually donate that hydrogen back to the water. This will function as the conjugate acid. And this will function as our conjugate base. And that's really all conjugate acids and bases is trying to say, more or less. All right, so a little practice. It's just going to be write the conjugate acid and conjugate base for each of these examples. I'm going to give you a moment to try it out. And basically what I would do is for the conjugate acid, one trick I like to do, or something you could probably just do, is you want to add one H plus to each one of these compounds. And then you find out what the formula you get is. And then that will basically be the conjugate acid of all these. And then same thing for the conjugate base. You could actually just simply remove an H plus. So this one is going to be add an H plus. This one is going to be remove an H plus. And then that will probably be the most straightforward way. You could probably get the conjugate acid and conjugate bases of each one. So take a minute or two and try and determine the conjugate acid and conjugate base for each one of these examples. All right, so I'm going to start going over some of these problems. If you haven't finished all of them, just try to follow along. So if I were to write the conjugate acid of this fluoride ion, what I could do is just add an H plus to the fluoride ion. So if we do that, the charges will cancel out. We can pair them together, and then our conjugate acid would be HF, which would be hydrofluoric acid. So our final answer would be that. This next one, we have NO3 minus. I can really just do the same thing. I'm going to add an H plus. So I can do an H plus and then NO3 minus. And if we do that, we can combine them together. We can get HNO3. And so this is going to be our conjugate acid, which is going to be nitric acid. This next one, it is HCO3 minus. It looks a little bit big. You might think everybody has a hydrogen, but you could add another one. So I can do H plus here and HCO3 minus. If I combine them together, I will get H2CO3. And this is going to be our conjugate acid. Finally, we have HSO4 minus. What I can do here is I'm going to add one other hydrogen, H plus to it. So I can do H plus and HSO4 minus. If I combine them together, I would have gone H2SO4. and that's going to be the conjugate acid. Moving on to the conjugate base of each one. So like I said in the top earlier, I said what we can do is we can remove the H plus. And so if we remove the H plus, we can just basically determine the conjugate base from there. So we know that if we remove an H plus from H2O, that means we're also going to be overall having one more electron than protons overall. So as a result, we would end up getting something like OH minus, which makes sense. The conjugate base of water would be the hydroxide ion. And if we were to combine them together, so if we were to combine OH minus and H plus, we would basically get H2O again. The next one is NH4 plus. This is going to be the ammonium ion. So what I can do here is I can take away one H plus, and then that would give us our conjugate base. So if I were to take away one H plus, then we'll be left with NH, and we took away an H plus, so we're going to remove one of those H's, so we have NH3. We also took away that plus charge up there, so we can take away that plus charge up here. So this is like +0, which we don't really show. And so because of that, our conjugate base of the ammonium ion is just going to be ammonia, which is NH3. The next example is going to be H3PO4. I can do the same thing. I'm just going to remove one H plus. So if I were to remove an H plus, then I would get H2PO4. And because we also took that positive charge away, we're also basically short one proton. So as a result, we're going to be having a total charge of -1, which makes sense because if we were to go in the backwards direction, combine it with H plus, we would get our original formula. So we'd get H3PO4 again. Finally, we have CH3COOH. This is going to be acetic acid or vinegar. What I can do again is I can just take away the H plus, and then we will be left with our conjugate base. So I can do CH3, COO, and then I will remove this H plus. So I will be left with CH3COO. We took that proton away, and as a result, we are left with an overall -1 charge. So the conjugate base of acetic acid would be the acetate ion. All right, so some additional practice. I want you guys to try and determine the acid, the base, the conjugate acid, and the conjugate base of each reaction. So I'm going to give you another minute or two to try and identify it all. So this goes back similarly to the example a few slides back. All right, so hopefully that was enough time to try and identify some of these bases, acids, conjugate base. So going over this first reaction. So going over this first reaction, we have NH3 plus H2O gives us NH4 plus and OH minus. So what I like to do to determine what is the acid, what is the base, is compare the reactant. So compare this portion and compare it with the product. And then you basically want to see what changed. So if you look at what changed, we can see that this NH3 gained a H plus. So in other words, this accepted the hydrogen. Whereas H2O, if you compare it to the product, it actually lost one of its hydrogens. So this is going to be the hydrogen H plus donor. And so following those definitions, we would be able to determine that NH3 is going to have functioned as our base. And because H2O donated the hydrogen, is going to function as our acid. Now, if we look at the product and we kind of pretend like it's going in the reverse direction, which technically it probably is, we can see that NH4 plus compared to NH3 is going to be able to donate the hydrogen, the H plus, back to the hydroxide ion, the OH minus. And because it's going to be able to donate that proton back, so this is going to function as our donor. And as a result, the OH minus will have accepted the proton so that it becomes H2O because it gained an H plus. So OH minus function as the H plus acceptor. Because of that, this is going to be the H plus donor. Therefore, it's going to have functioned as our acid. And because it is going to be the product that is formed after, we indicate this is going to be the conjugate acid. And because OH minus accepted the proton, is going to have functioned as the base. And because it's going to be formed in a product, we're going to show it's going to be the conjugate base. This next example is a little bit more, it's more or less the same difficulty, I would say. So we have CH3OH. You'll learn that this is going to be known as methanol. So methanol will react with water to produce the CH3O minus, which is going to be the methoxide ion, and H3O plus, which is going to be the hydronium ion. So if we compare the starting material and the product, what we will notice here is CH3OH, methanol, has donated one of its hydrogens over to water. So that's how we ended up getting H3O plus in the product. And the CH3O minus has lost one of its hydrogens. Therefore, it's going to be the hydrogen donor because it donated away its hydrogen. So I'm going to label these again. So CH3OH gave away its hydrogen. So this is the H plus donor. This one accepted it, so it's going to be the H plus acceptor. Now, if you look in the reverse direction, we'll see that the H3O plus can give away its H plus back to the methoxide ion, the CH3O minus. Because it gave it away, it's going to be an H plus donor. And CH3O minus is going to be the H plus acceptor. And because of that, H plus donor means it's going to function as the acid. This is going to function as our base. This is going to function as our base. And this one will function as our acid. And remember that this is going to be the product that is formed on the right side. So we're going to indicate the right side as the conjugate acid and conjugate base. All right, finally, one more definition. Um, this is going to be covering Lewis acids and Lewis bases. So this is probably going to be the best definition or the most broad definition that covers every single type of definition of an acid or base. And basically, it describes a Lewis acid as something that is going to be an electron pair acceptor. And a Lewis base is going to be something that is going to be an electron pair donor. So a more formal way, I guess, to represent an electron pair acceptor is that we can write the Lewis acid is going to function as the electrophile. In other words, the suffix phile means like lover. So in other words, it's going to love electrons, or it will be able to accept electrons very easily. And the Lewis base is going to be an electron pair donor, which is going to be called the nucleophile. Meaning that it really likes to attack a nucleus. In other words, well, that's basically it for a nucleophile definition. So a Lewis acid and a Lewis base, I will say that it is slightly harder to me to identify them just by looking at the reaction itself. I find it's easier to identify them if you draw the structure, the Lewis structures of them, and visualize what is happening. So if you look at BH3 and NH3 forms something like NH3BH3, it's kind of hard to tell what's going to be the acid or what's going to be the Lewis base. So the easier way to do it is you draw out the Lewis structure. So we can see on the left side, this is going to be BH3. This is going to be NH3. And then this is going to be NH3BH3. So following this definition, a Lewis acid is going to be one that is going to be an electron pair acceptor. We can see here that on the left side, BH3 is going to be accepting the electron pair from NH3, this electron pair. And because it accepted it, it's going to function as the Lewis acid. So I'm going to write La. Whereas the Lewis base, in this case, is going to be NH3. So NH3 is going to be donating that electron pair, this one right here. Once again, it donated it to BH3, and therefore it functions as the Lewis base. So, like I was saying earlier, it's kind of hard to visualize which is Lewis acid, which is the Lewis base, without having to draw the Lewis structures. Another way you might be able to possibly tell is if you look at the partial positive and partial negative charges. You could probably also potentially deduce which one's going to be the Lewis acid and which one's going to be the Lewis base. So if you were to draw the partial positive, partial negatives, what you can see here is we know hydrogen is more electronegative than boron. So therefore, it's going to be partially negative up here. It's going to be partially positive next to boron. And the hydrogens are also going to be partially negative. So in other words, they're all pulling electron density away from boron. So the partial positive charge around boron is pretty strong. Whereas we have NH3, nitrogen is going to be more electronegative than hydrogen. So this is going to be electronegative. It's going to be able to pull away electron density away from the hydrogens. So these are going to be a little bit more partially positive. And because of that, we know that opposites attract. So we know that this very electron-rich NH3 is going to function as the one that can donate its electrons to this BH3 right here. So if you like kind of like pair this up, that's how we end up forming this product right here. We get that bond forming because the NH3 is going to be able to attack that electrophilic boron. All right, so a little practice. Try and identify which one is going to be the Lewis acid and which one is the Lewis base. And I've kind of drawn a little hint here. I did not show the lone pairs on all of them. So hopefully that makes it a little bit more clear. And I'll give you guys like about 45 seconds to try it out. All right, so the Lewis acid in this case is going to be the one that is going to be the electron pair acceptor. So if you were to draw like the partial positive and partial negative, what we can see here is we know chlorine is pretty electronegative. So I can draw like these partial negatives all around here. And aluminum is not nearly as electronegative, so it's going to have its electrons taken away from the chlorines, the electron density. Whereas if we look at this molecule on the left, we can see there's going to be Cl. There's going to be a lot of lone pairs hanging around it. And this is going to be pretty electronegative. This is going to be like slightly partially positive. And because of that, it can donate this electron pair and basically attack the aluminum. And because of that, it forms this bond right here. So we have a partial positive, not a partial positive, we have a positive charge here, and we have a negative charge on the aluminum to form that bond. So this is, this left one is going to be our electron pair donor. So electron pair donor. This one is going to be the electron pair acceptor. In other words, the left molecule is going to be the nucleophile, and then the aluminum trichloride or aluminum chloride is going to be functioning as the electrophile. So we could say that this left one is going to be the Lewis base, and this right one is going to be the Lewis acid. And there's not really a conjugate acid or conjugate base in this example. All right, so now we're moving on to like the last part of this workshop. It's just going to be calculating pH and pOH. And so the pH scale ranges from 1 to 14, with 7 becoming the neutral pH. And a neutral pH is going to be like water. Water has a pH of about 7. Pure water, that is. So the pH range between 1 to 14, know that the pH between 1 and 7 is going to be acidic, whereas a pH between 7 and 14 is going to be considered basic. So how do we calculate the pH? What we're going to do is we're actually just going to take the negative logarithm of H3O plus. H3O plus is in brackets, so we're going to be looking for the concentration of H3O plus, and usually either one of those will be given. And the other way is if you want to find out the concentration of H3O plus, we can just take 10 to the negative pH of the solution that we're given. So like algebraically, how they got here is kind of like, if they have the negative sign right here, we could kind of technically move that over. So you can get like negative pH is equal to log of H3O plus. And then remember that log is going to be base 10. So we can do 10 to the negative pH is equal to 10 to the log of the concentration of H3O plus. And the base 10 and the log will cancel out, and we will be left with the concentration of H3O plus gets us 10 to the negative pH. And so that's basically how they derived this other formula from the pH formula. So calculating the pOH is really similar. You really actually just replace the H with OH anywhere you see it. So it's pOH is equal to the negative log of the concentration of the hydroxide ion. And the way you calculate the hydroxide ion is you really just take 10 to the negative of the pOH. So it really is like the same formula, more or less. Okay, so some examples of calculating pH and pOH. Before I go into calculating them, I should mention that the pH and the pOH should add up to 14. So let's say a solution has a pH of 7.1. What is the pOH of the same solution? What we could do here is we could really just plug it in and find out what we get for our answer. So we do pH is equal to 7.1 plus pOH that will get us a total of 14. To isolate pOH, we could subtract 7.1 from both sides. And we should get an answer of 6.9. So the pOH is going to be equal to 6.9 if the pH of that same solution is 7.1. You can always check, because if we add 6.9 and 7.1, then we should get 14. The next example, if a solution has a pOH of 8.9, what will be the pH? So this is just the backwards or the other way. So I could just write what we do know, what we don't know. What I could do is just put pH plus 8.9 gets us 14. So 14 minus 8.9 gets us 5.1. So the pH of the solution in a solution that has a pOH of 8.9 would be 5.1. And yeah, so these calculations are pretty straightforward. All right, so these last bit of problems, it's just going to be these 4 problems. It's going to be combining both the formula you see on these slides. So the pH is equal to a negative log of H3O plus, and H3O plus is equal to 10 to the negative pH, along with the OH versions of it. And then we're also going to be combining some concepts using the pH and pOH equals 14 formula. And yeah, so try and solve all these problems. I'm going to give you guys about 2 minutes, and then I'm going to go over them. All right, so for the sake of time, they're coming a little bit close towards the end. So I'm going to just try and go through all 4 of these problems. And 4 problems in 2 minutes is a lot. So just try and follow along. So the first problem, a solution has a pOH of 3.8. What is the concentration of the hydroxide ion? So what I can do is, if we know that formula from back a few slides back, we know that the concentration of OH minus is equal to 10 to the minus of the pOH that is given. So if you plug that into our calculator, we could just do 10 to the minus 3.8. And then let's see what answer we get. So I am getting an answer of 1.584 times 10 to the minus 4. If we take into account significant figures, then probably around 1.6 times 10 to the negative 4. And then we're looking at concentration. So the units that we will be using for concentration should always be in molarity. So we put in M as our final unit in the answer. The next problem is, what is the pH of a solution that has a concentration of, that has a H3O concentration of 2.30 times 10 to the negative 4 molarity? So I'm going to plug into the formula. pH is equal to the negative log of the concentration of H3O plus. So what I will do is put into the calculator negative log of 2.30 times 10 to the negative 4. And I am getting an answer of about 3.63. 3.638, taking into account sig figs, probably around 3.64. And it makes sense because our pHs in most pretty much should always be between 1 and 14. 3.64 is between 1 and 14. The next question is, what is the concentration of hydronium ions in a solution that has a pOH of 9.5? So if you remember from the previous slide, that the pH plus pOH should equal 14. So we do pH plus 9.5 is equal to 14. And therefore our pH should equal 4.5. And then if we plug into that formula we saw earlier, it's going to be 10 to the negative pH. So I'm going to do 10 to the negative 4.5. And we should get a concentration of 3.16 times 10 to the negative 5 molar. Finally, we have a solution has a hydronium ion concentration of 1.9 times 10 to the negative 9 molar. Is it acidic or not? So what we can do here is calculate the pH. So I'm going to do pH is equal to negative log of the hydronium ion concentration. So I'm going to do 1.9 times 10 to the negative 9. If I plug that into my calculator, we should get an answer of 8.72 is equal to our pH. So the question asks, is it acidic or not? Remember that acidic is going to be between a pH of 1 to 7. And basics are going to be between 7 and 14. 8.72 is between 7 and 14. So the solution is not acidic. And yeah, it's going to be a base. All right, so that comes to the end of our workshop. If you guys have any questions, yeah, so you can schedule for tutoring at the link here. If you haven't already joined the Virtual Science Center, you can self-enroll, and you can always email us any questions you might have. So yeah, thank you all for coming by and listening.